All right, what I'd like to do today is I'd like to go over number 34 on page 103 in Giancoli. I like this problem because it illustrates some interesting things, but it is somewhat of a doozy, so I wanted to go over that with you. Okay, so the idea is on 34 we've got three boxes on a frictionless surface, and we're calling them A, B, and C. And we are putting a force on it here that your book is labeling F, and it's, at least at first, it's not telling us what it is. It's just telling us that we're putting a force on it. And, okay, let's go through this. So part A says, draw a free body diagram for each block. All right. So I got three blocks. I'm going to draw a free body diagram for block A, free body diagram for block B, free body diagram for block C. All right, and we know, let's start with the easy part. We know that all of these blocks have gravity, and they all have normal. So this is the force of gravity on A, force of gravity on B, the force of gravity on C, and then we're going to have the force normal on, that's C, the force normal on A, and the force normal on B, or on, well, I can't count my letters today, A, B, and C. All right. All right, so there we have it. So that's the easy part. And now we say we've got this force that the book is calling F. I might call it the force applied, just so that I have a label for it. Or we could just, maybe it's probably going to be easier. We'll just call it F in this case. So the force of F is acting on A, and it's pushing A this way. It's pushing A forward. So I'm just going to call that F. Now, what's interesting, this, at its core, this question is a question that's illustrating Newton's third law. Because the idea is, how does that force get to B? Well, this force, its applied force, doesn't act on A. Doesn't act on B. It only acts on A. So how does the force get to B? Well, A has to push it. So we're going to say that there's a force on B from A, and I'm going to call that force BA. And that's how the force gets to B, because A pushes it. But Newton's second law says every action force has to have an equal and opposite reaction force. So if I have the force of B on A pointing this way, I also have to have the force of A on B, but that acts on A. And you'll notice I'm trying to color code this here because these two forces are equal and opposite. Well, how does this force get to C? Well, there's a force on C from B. And again, that has a reaction force, the force on B from C. But you'll notice that this is done in such a way that if all these blocks are moving forward, they all have to end up with a net force that's forward. So I'm going to call this the net force on A, which is forward. I have a net force on B, which is forward. And I have a net force on C, which is forward. Okay, so that's part A. Part A was to just draw our free body diagrams. That's what we've got. B says to calculate determine the acceleration of the system in terms of MA, MB, and MC. When it says determine the net force, it hasn't given us any numbers yet, so it wants an algebraic solution. So if we go ahead and do that here, so part B, let's go through what we know here. Well, we know in this case the net force on A is going to be equal to the one that's pointing in the same direction minus the one that's pointing in the opposite direction. So the force minus the force of AB. And we also know that that's equal to the mass of A times its acceleration. And I'm not calling this the acceleration of A because remember, if I'm pushing this, the whole system has to accelerate at the same rate. So I'm not calling this AA because it's all accelerating at the same rate. All right, if we just go along the line here, we can say that the net force on B in this case is going to be the one that's going this direction, right? FBA minus the one that's going this direction, which is FBC. And that's going to be equal to the mass of B times A. There we go. And then we're going to have one more here. This net force of C only comes from one force. So the net force on C only comes from FCB, which is also equal to the mass of C times A. All right. Okay, so what are we going to do with this? Our goal is to come up with an equation for, or an expression for acceleration. So essentially what we have is three equations with three unknowns. What we're going to do is we're going to kind of solve this recursively, and we're going to say, okay, I know from here what the force of FCB is. And we know that these two forces are equal and opposite, so they have to be equal. So what I can do is I can take that and plug that in here, right? I can just rewrite this equation, but I can say, what is FBC equal to? Well, it's equal to MC times A. So this minus that equals MB times A. So again, this equation is equivalent to this equation. I've just plugged the expression here in for that. And then I'm just going to rearrange it a little bit. So I can say that FBA equals, if I add an MCA to both sides, it's MBA plus MCA. Well, that's cool because then I can take this whole thing and say, okay, FBA is the same as FAB, and I can plug that into this equation. So now I've got that F minus this whole expression minus the quantity MBA plus MBC equals MBA plus MBA equals MA. And again, just to make it neater, I'm going to go ahead and add this quantity to both sides. So now I have F equals MAA plus MBA plus MCA. And just to make it even simpler still, we're going to factor out an A from this whole thing. And we're going to say this is MA plus MB plus MC. Pardon my, let me write that a little bit easier to see. It's MA plus MB plus MC, the quantity, times A. So just double check for yourself, convince yourself that if I distribute the A out through here, I get the same thing that's there. And this is kind of neat if you take a look at it, because this is saying, this is Newton's second law here, right? F equals ma. It's just that my mass is all the masses combined. So if I wanted an equation for acceleration, then I get A equals F over all these masses added together. So that's what B wants. C is asking for the net force on each block. So essentially, it's really just, we've done all the hard parts at this point. It's just asking for, in this case, right, we've got, well, so let's do this here. So C, we can say that the net force on A equals, we know it's MA times A. But we just found that A is this junk. So when I plug in this junk into there, I get that the net force on A is MA times F over MA plus MB plus MC. Or, put another way, it's the force, sum of forces A is equal to the force times MA divided by MA plus MB plus MC. And again, this is intuitively interesting because this is saying what you'd expect is that the net force on A is going to be whatever fraction of MA is out of the whole mass, right? So if, for example, if you look at when we put numbers to it in part E, it's saying, imagine each of these are 10 kilograms. If each block is 10 kilograms, it would make sense that the net force on A would be 10 divided by 30, so 1/3 of the whole force, right? The net force on the A, 1/3 of the force is coming from that. And you see where we go from here. We can say that the force, the sum of the forces on B is MB times A. And again, we know that A is all this junk, is F divided by MA plus MB plus MC. So again, we have that the sum of the forces on B equals, we're just going to get the same thing over and over again. MB over MA plus MB plus MC. So again, you'll see that a third of the force went into the net force on A. Once again, if we treat each of these as equivalent, a third of the force is going to go be the net force on B. And if I were to do this for C, I'd get the same thing. I'd get the sum of the net forces on C would be F times MC over MA plus MB plus MC. So there's that. And from there, you can go ahead and plug in the numbers that you're given. And again, the what this is trying to show is a couple things. It's trying to show that the way that a force gets transmitted through a system like this is due to Newton's third law. Pardon me. Again, this applied force never acts on block C. It just has an action-reaction force on B, and then there's an action-reaction force on C. So that's one thing it's trying to show. It's trying to show that we get what we would expect, namely that if you considered this whole system up here as having one large mass, I get F equals MA with that one large mass. And also that each net force gets a weighted average of what that force should be connected on. What that in our case, right, that each force gets 1/3, each net force gets 1/3 of the applied force. And so again, it's a little there's a lot to that. It's a little bit of an involved problem, but I think it's interesting to see how Newton's laws give what in the end is really a rather elegant result, even though it was kind of a mess to get there. All right, so that's what we've got.